Hi, I'm Cedric, and I'm going to present to you a theory on the absence of spurious solutions for non-convex and non-smooth optimization. This is joint work with my collaborators at the University of California at Berkeley. In this work, we are interested in low-rank matrix completion. 2 years ago at NeurIPS, some authors could show that there are no spurious local minima in the Bureau-Monteiro formulation using least squares, provided that the matrices, sensing matrices, satisfy the restricted isometry property and a regularizer is added. We asked the question, what about if there are outliers in the data, which essentially means we are replacing the Gaussian noise with Laplacian noise, and we then obtain a least absolute value objective function. Now this is challenging because it is both non-smooth and non-convex. And typically, you can see here the motivation that numerical experiments, this allows us to handle sparse noise better using absolute value rather than least squares. Some applications include recommender systems and state estimation in power systems. Our approach is to define a new class of function, which is global functions. In other words, continuous functions and such that all local minima are global minima. And these have some nice properties regarding the composition of functions, change of variables, and also we should note that they encompass all the previously proposed generalizations of convexity. And so typically one of them, which was recently proposed, which dealt with decreasing paths. And here you can potentially have no decreasing paths. The strong property that they verify is this uniform limit theorem. If you take, instead of pointwise convergence, the uniform convergence, you can actually show that if you have a sequence of global functions, their limit has no spurious strict local minima. And this can be applied to the matrix completion problem, as you can see below. We take the least squares problem, which is at the bottom left, and then we take the LP norms with p going towards 1, and we gradually go towards this non-smooth setting, and we can prove something about it using this uniform limit theorem. And so to sum up, this allows us to have two different strategies for tackling this problem of completion and more generally for tensor completion. One, which is the proof 1 sketch here on the left, which involves uniform convergence, writing the optimality condition of the LP norm, and another proof strategy, which is to use the Clark derivative, which makes for a much longer and more technical proof, but also uses global function property.